the last day of class?
The 31st.
Wow.
I've been hearing whispers from people that they want, like, to discuss dropping a quiz or something.
Well, I could whisper all I want, but, I mean, I'll tell you the truth.
I don't think we have enough to, like, do it, but
Frankly, I don't know how many we have right now. See, the summer's so short, and 15 weeks is different. I don't know. I'll give it some thought. Okay. First, any questions about anything we've covered up to this point? We're into chapter 4 now. Did anybody have a chance to look at, I know it's not pertinent to the quiz, to the problems in chapter 4? Did you? This is where, it's called element of statistics, but where you're actually getting into something that has real meaning and application in the real world when you're doing VLSI processing or anything when you're trying to create components and you want to have a very good idea of how many of these, basically what percentage is going to be working and what percentage isn't. So this is important. And Tom Denny's PowerPoints that I put up there, they're very, very good on this one. But I'm going to go ahead and talk about a few of these things and do some of the problems. But whenever you're talking about the variance of a sample, so if you, if you have something, one of those things. Okay, if you have something where you have n items, and you're going to take out of there a small number n, and n is going to be much less than n. So we're going to take this sample here of n of them out. And you're going to look at this, and you can calculate things. And in the notes, in the power, how many have looked at the PowerPoint on this chapter? It's very, very clear. There's no, he's not doing a lot of discussion, showing things that are sort of abstract. He does prove some of these things. But when you do this, you get the sample mean. And I'm going to call it this, and that's just the sum of really x of I of the samples from I equals 1 to n, and it's 1 over n. And that's the actual sample itself. And then they create another random variable, x of I. And this represents that if you start sampling these things, but you do it, you basically, it's going to be a random process. You can sample, sample, sample. These are going to be something where it is not a fixed number. In other words, it's a random variable, the samples. And here, if you go ahead and get the sample, the mean of this, and he likes to do this, he's going to have like a bar over this thing. And that will be, if you take 1 over n, and then it's going to be really, or I should do it this way. It's the expected value of the sample. And this is the random variable. That will be, in fact, the actual mean of the samples. It's not as clear as Denny's notes, but you get the idea. That's this whole point. Now, when you get into this, the next thing you talk about, and this is where it gets a little more clear and important. If you take a look at the variance of these samples, the random variables, variance of the sample mean, variance of the sample mean, you can go ahead and write the equations for this but it basically comes down to, it's sigma squared over n, where n is the number of samples. And sigma squared is equal to the actual variance of x.
The true variance?
Huh?
The true variance?
Yeah, the true variance. I've got to say one other thing about this that should bother everybody. So if you know the true variance while you sample,
Yeah.
that's an obvious question if you just read through that. If we know the reason we're doing this is we're going to, as we go downfield with this, we're going to find out that we can actually get a pretty good estimate of that. Now, this shows you that this is the variance of the mean, is what this is. We're going to also talk about something, and these are the variance of the sample mean. We're going to talk about the variance of the sample mean, but we keep going down that road and eventually get to a point where we talk about, I don't know if you've heard this in any other classes, I doubt. Right now, that's assumed. If you don't know it, we're going to be talking about something where we're going to get a variance of this variance, which gets a little bizarre here. And we're going to find out that that itself, when we go through the proofs, this is in the next couple of sections, the next 3 sections, we'll be able to do something where we get what's called a confidence interval and how confident you are in the information you have. That's critical. And that's one thing I've alluded to. In the real world with polling, the confidence interval is a wild guess, and it's usually really off base because any of the assumptions you need to actually make this work are usually not, I mean, the premises aren't usually there in the real world when they do these polling. Now with VLSI technology, does everybody know what I'm talking about? Very large scale integration. When they make chips, anything like this, they may have 10,000 to 1,000,000 different transistors that are used to build a chip that's going to do anything you can imagine it, ASIC, anything like that. Well, when they're doing these processes, they don't make one, they make millions and millions, and they have to find a way of figuring out in real time what percentage of those are going to be actually functionally correct and how to go about. Once they get that, they can do all sorts of things to identify what could be causing malfunctions and all this stuff. But the other thing I got to tell you is nowadays you should consider this if you're interested in something that's very valuable to manufacture, and that is built-in self-test. Have you heard this term? Anybody? You have built-in self-test is literally where they create circuits on the chips that are going to be testing that circuit to make sure that it's functional. Now, there was a guy, there's 2 people that were here. One was Chuck Stroud, and I think the other is Vishwani Agarwal. They both retired, and I don't know who's doing that now, but if you're interested in any kind of very large scale manufacturing, basically solid state physics and you take a microelectronic lab, don't you? Or not? You take? Do you take?
Visual electronics?
No.
You're talking about like the weight, like the wafers class?
Yes. Do you take that or not?
I think that's one of the ones you can take.
All right. Well, if you go down that route, and this is sort of at a point now, I'm just mentioning this because this is kind of important. At least you have an idea of your options. Everything now is still silicon-based technologies for all the VLSI components, but you've heard of 3,5 compounds like gallium arsenide, right? Gallium nitride, things like this. They have a lot of benefits. First of all, some of them are much faster, and second of all, the threshold voltage, like for silicon, it's 0.7 volts. For gallium arsenide, I think it's 0.3. If I'm wrong, correct me, roughly. But you can do things where these are solid state compounds, but they're going to, at least theoretically, they can outperform silicon. The problem is the cost. So anytime you're doing something like that, it can get really cost effective. However, all the stuff that we're talking about here in the built-in cell test that you'll be doing, that has a direct application to that type of thing. Is anybody here? I don't know if anymore. It used to be VLSI. Everybody wanted to get into solid state, into VLSI processing and all that, because that's where all the money was. I mean, you go out to California, you could retire in 10 years if you got in with a good company. Nowadays, I'm not sure how much of that's going on. Did anybody ever mention to you how, I guess, valuable it is to get a focus on microelectronics and solid state physics and VLSI? No. I don't even know what they tell you anymore. I mean, when I teach EMAG, I try to give people a very good idea of what in the defense sector or communication sector, what's available to you as job opportunities. But anymore, I don't know if they, in your classes, do they tell you the kind of jobs to expect? No? Okay. Anyway, back to this, let me stay on top. So this right here is saying something about the variance, and it's for, when in the assumption for that formula to work is that the number of samples is very, very small, or I should say the number, small n, is very, very small compared to large n. If it isn't, then you have to do something different. And this is for n much, much less than capital N. If it's not, if n, I should say, if n is only a little bit less than capital N, then this formula, the variance of x, will be equal to, it starts with that sigma squared over n, but then you're going to get two terms. You're going to get n minus 1, and then it's going to be capital N minus n. And that will be the variance. And that's actually when you don't do replacement either. I didn't say this, but for this one, you don't have to, like if you take a sample, you don't have to put it back in there. Take a sample, put it back in, if this condition is true. If we've got this, and then we don't replace the sample, this is much said without replacement. Then you have to use this formula to get the variance. But the real thing about this is, so what? What does it mean to me in terms of real problems? Well, the square root of the variance, that's the standard deviation. And that's something that will become important because if you remember, and by the way, for a very large number of samples, most of these things turn out to have a Gaussian profile. And if this is the mean, you're going to get something like this. And you're going to find that, I should do it this way actually. The standard deviation, or square root of the variance of x, which is the standard deviation, becomes important in understanding the amount of error and significance of it. And I'll also tell you how many samples you need. Okay. I could go through the proof, but I don't think it's work. So there's an example. Oh, but this is actually the problem I assigned. I'm going to go ahead and do this one. I know you're anxious for your quiz, but I want to do this one. I will consider doing something like dropping it, because I'm not sure what I'm going to do. So I assigned 4.2.1. Now, that one required you to manually add up a bunch of values and then take the average. Well, it's kind of boring, but we'll talk about that. Do you know what our final exam is?
Where can I look that up?
Huh?
Where can I look that up?
It's on the 7th at 8
If you go to Canvas, I think they, or you can just type this in, final exam schedule, summer 2026 Auburn University. It'll pop up. But it's on Canvas. Unless things have changed. But it's almost always there. The reason I want to get that, I'm curious about that. I don't think anybody's going to have two final exams the same day, but sometimes you do. Sometimes they, if that happens, what I want to do is see if I can give you guys enough, or do anything to give you extra time if you need it. All right, so for 4-2.1, he's got what, 9 samples there?
Mm-hmm.
And they ask for the sample mean. That's adding them up and simply dividing by the number. And I frankly didn't do that, but for that one, well, I think I put the solutions up on this one for this problem. Anyway, if you do that, you're going to get a value. Then he says, and I don't know exactly what it is, but that's almost inconsequential. Then he said, if the calculator produces 3 digits that are random numbers uniformly distributed between 0 and really 1, find the variance of the sample. So here's what he's saying. Here, remember, the number of samples we have is 9, and he's going to say from 0 to 1, we have, basically a flat probability density. This is going to be the probability density function for the actual values. I'll call it f of x. Doesn't really matter. And this value would be 1. So it goes from 0 to 1. Now, this is kind of important. So in there, now they want the variance of the sample mean. So, matter of fact, let's use. And here, there's nothing about replacing anything. However, in the solutions manual, this is one point I'm going to make. In the solutions manual, he uses a formula that has to do with sample without replacement, but in that statement of the problem there, it doesn't say that. It just, matter of fact, let me just read it directly so there's no misunderstanding. The first thing he says, a calculator with a random number generator produces the following sequence of numbers. There's 9 numbers, add them up, divide by 9, you get the average. That's a no-brainer. Next part, and I would not ask that on a test or a quiz. I can tell you that right now. Next part is, if the calculator produces 3 digits that are uniformly distributed between 0 and 1, it's 0.999, but really 1, find the variance of the sample mean. All right, we have 9, we've taken 9 things, and he uses the wrong one in the solution manual that I posted the first day of class, basically. In the solutions I posted on OneNote, it is the right value. It does it the right way. So for this one, and you'll need to know this formula, you know that the variance of x, with this, is going to be equal to sigma squared over n. So here, we need sigma squared of this. Remember, sigma is true variance. Well, and this is where people will forget. Remember, that's a uniform distribution. Do you remember that the actual variance of that, or sigma squared of that, would be equal to 1/12, and the way it was put before, times delta x squared. And if this is the value of x, it's really the spread or the difference. And we proved that one time, probably about 3 weeks ago. Do you all remember that class? I mean, if you wanted to get, to do this, first, and I'm making this point because I can see people forgetting about this on quizzes, tests. If you look at this thing, and that's the density function, this value is one spread from 0 to 1. Now just think about it. If you wanted the mean value of this is the true mean of that, what would you do? Just tell me, in your own words. The mean. What do you always do? It's, if you want the expected value of any function, f of x, right? Doesn't matter what it is, what do you always do? You do an integral, right, over where the function exists, and you, well, I better call this g of x, and you take the function you want the expected value of, then you have to multiply it by the probability density function. And if it's discrete, it's going to be a sum. If it's a continuous density function, it's an integration. So then it would be multiplied by the probability density function dx. Over here, if you wanted the mean, technically would be the integral from 0 to 1 of the value you want the mean of. This is the expected value of x, so it's just x. The probability density function for this is 1, isn't it? And then, so it's just dx, or that's x squared over 2, or it's 1/2. So we got that. Now, if we wanted the mean squared value, and I can see people kind of stumbling around this. If I wanted the mean squared value, or I wanted the expected value of x squared for this one, I'll do it right here, actually. So x squared bar, that would be the integral of x squared dx from 0 to 1. And that, obviously, is going to be equal to x cubed over 3 from 0 to 1, or it's 1/3. Y'all agree with that? All right, finally, now if you want the variance of this, and I'm going to just call it the variance of x, that's equal to x squared bar minus x bar squared, and that's going to be equal to 1/3 minus, and that would be 1/4, and that would be 1/12. Can everybody follow me on this? Just so you know all parts of this. Anyway, back to this thing. The true variance of this one is going to be 1/12, because the spread right here, the delta x is 1. So we have sigma squared is equal to 1/12. And for this part, he wants the variance of the samples, right? We have 9 samples. We know the true variance, so it's going to be equal to 1/12 divided by 9, or 1/9 times 12. That's what, 1/108? You all follow me? It's straightforward. What's the next part of the problem?
How large should the sample size be in order to obtain a sample mean whose standard deviation is no greater than 0.01?
Okay. This one you've got to pay attention to. And the wording gets you. So they said the standard deviation, is that right? Is 0.01?
Yeah.
All right, standard deviation is square root of the variance of x, and that's the sample. So I know the variance, this is something that he says it's 0.01.
Yeah, no greater than 0.01.
And here, since there's no information at all about the number n, total number, it's just got that density function. This is going to be sigma squared over n, or n itself would be equal to sigma squared over 0.01 Oh, wait a second, hold. Take it back. This is the square root of the variance. And this is 0.01, right?
Yeah.
So that means if I get the variance of x, that's actually going to be really 10 to the minus 4 because 10 to the minus 2 squared. Follow? So that would be the variance, and that equals sigma squared over n, or n itself is equal to sigma squared, which is 1/12 squared over 10 to the minus 4th. God. So you got what? 10 to the 4th, and you're going to be dividing by 144, and I don't remember what that is. I know I did this, and is that 833?
Yeah,
I think it is.
that's what I got when I worked it out before.
This is straightforward, just an application. But here he did one thing that he's going to change up. He actually defined what the standard deviation was exactly. It wasn't in terms of 5% of the mean or anything. He's going to start doing that shortly. That was that problem. And then 4.2.5. Get rid of this. Anybody find out when the final exam is?
I think it looked like it was that 7th that he said.
July 7th?
August.
Or I mean, August 7th at,
8 AM.
Yeah,
oh,
8 to 10, yeah.
August 7th, 8 a.m. Well, you can bring coffee if you want. All right, for this one, 4-2.5, go ahead.
In a class of 50 students, the result of a particular examination is a true mean of 70 and a true variance of 12.
All right, so we got a true mean of 70 and a true variance of what?
12.
Okay, 12, go ahead.
It's desired to estimate the mean by sampling without replacement a subset of the scores.
All right, so now I'm just going to put the formula. So this is the variance of the samples is equal to, this is sample without replacement, so it's sigma squared over n. And then you're going to have capital N, the number of samples, or the number, total number, minus the number that you actually sample. And then it would be n minus 1. I want to put that formula down. This is the one that we're going to be used, and it's you're going to have to know that. I'm going to tell you, you're going to have to know the prior one and this. With me, class? Just so I'm clear. And say that last part again.
No, that was it. Without replacement a subset of the scores.
Okay, and he's looking for the value of n, right? For some reason.
Find the standard deviation of the sample mean for the 10 scores.
Just the standard deviation. All right. So what he really wants is the square root of this. And this is part A. So that means the standard deviation would be equal to the square root of the variance of x. And that's going to be equal to simply sigma times the square root of n minus n over n minus 1. I'm just putting it there, and I factored out the sigma squared, so you know, the square root. And from that point, you're going to end up with, maybe I should have left it in there, but I'll put it back here. So you're going to have square root of 12 times, and it's 50. And here, for this one, n equal 10, right? So there's 10 we sample 10 of these items out of a total of 50, so that's gonna be 40 over 49. Now, what does that come to?
0.9897.
No, wait.
Where did the little n go in the denominator?
Did you screw it?
Good point. It is, that should be it, isn't it? I don't know what that is. What did you say?
I said 0.9897.
Is that right?
Yeah, that's right.
So that's the standard deviation of the mean of the samples. It's, the wording will get you on some of these parts. What's the next part of that one?
How large should the sample size be for the standard deviation of the sample mean to be 1 percentage point out of 100?
This one, pay attention. So he's saying the standard deviation of the sample mean, right?
Yeah.
All right, so it is 0.1% of, so the square root of the variance of the sample's mean is going to be, is it 1%?
1%.
All right, so 1% is going to be really 1 over 100 of what value?
Of 100?
It just says 1 percentage point out of 100. The standard, how?
That's just 1.
Yeah, it's 1.
Right. Okay, so basically, 1. And then I can, well, 1 squared is 1, so I get the variance here of x is equal to 1. Is equal to then, I'm going to take that whole thing again. Now, for this one, you're going to have sigma squared, so you have 112. Then we're going to have n, which is 50 minus n over, and here you're going to have n, small n, and this is going to be 49. And now we're going to solve for small n. So let's see here. We're going to have 49n is equal to 49n, pardon me, times 12 is equal to 50 minus n.
Was it supposed to be 1/12 or 12?
Pardon me?
Was it supposed to be 1/12 or 12?
12, pardon me. You're right. Not bad on that one. You're absolutely right. So 49 and is equal to 12 times 50 minus 12 n. That's going to be 61 n 12 times 50. And that's n equals 12 times 50 over 61. Can you tell me what that is? I just
9.84.
9 point what?
9.84.
Well, you can't have.
Yeah, so you have to
0.84,
round
it's
up
gotta
to
be
10. Yeah.
Is that the answer?
Yeah, it's 10.
All right, so this technically is 9.84, and you gotta round it up to 10. Okay, another part to that one?
That was,
That's it.
Part C is how large should the sample size be for the standard deviation of the sample mean to be 1% of the true mean?
Okay, so then for the last part, over here. I'm gonna tell you this stuff, you see, he's talking about standard deviation being 1% of something and stuff like this. People often forget to put the variance into that. Standard deviation, square root of variance. Just remember that one thing. So For this, it says, so standard deviation is going to be equal square root of the variance of x. And is equal to, say that again?
1 percentage point of the true mean.
All right, so that's 1/100th. It's 1% of the true mean, right? And the true mean was 70, right?
Mhm.
So times 70. Or 0.7 is the variance, square root of the variance of x. And that means 0.7 square root of 0.49 is equal to the variance. And this is going to be equal to sigma squared, I'll write it down first, sigma squared over n times capital N minus n over n minus 1. I'm just rewriting that, and I'll put the values there. And for this one, that's going to be, I think it's 0.49 here is equal to 12 over n. It's 49, and that's going to be 50 minus n. Unless I did something wrong, I think that's right. Can you agree with this, class?
Mhm.
You don't, I mean, we can multiply, let's see, 49 times 0.49 times n, and basically you solve for the whole thing, so what do we get for this? N times 0.49 times 49 here is equal to 12 times 50 minus 12n. Take it to the other side, so we've got n equal 12 times 50 over, and then you're going to have 12 plus 49 times 0.49. I'm just writing this down for completeness. I probably didn't need to do that, but I'm just showing you mathematically, this is not going to be one of these transcendentals kind of problems or where you get a quadratic to solve. It's an exact value. You're going to see we will need to solve quadratics and equations where you need root solvers coming down the road. But what is that?
Brown says 17.
About anybody? Is that right? Was there another part to that one? I want to tell you that that's the simple stuff right there. The next, just going to touch on this before I give you your test. The next thing we're going to get into is the variance of the sample variance. Now, I'm going to, for the sake of time, just put it on the PowerPoint. And I want to mention something about this too. This one has got something that will really confuse you, and I'll point it out. It has to do what's called the unbiased and biased values of the variance of the variance. And it can drive you a little nuts. I assume everybody can see that, but the actual it's loud, show. All right, those were those two homework problems. They're very simple, straightforward, but you have to at least get familiar. You're going to need to know those two formulas for sampling large without replacement, or if it's a very large sample size. I mean, a very large population size and small set, and N is small compared to the total number, and the one where you sample and not replace. And those two things you have to be familiar with for the actual variance of the mean. Now, this is going to be the variance of the variance. And so he shows 1,000 transistors and the value. We know how to estimate the mean. We just did that. And again, it assumes you know the true mean, which I don't like. And it assumes that you actually know the variance. So by you doing this question, these things are going to be, all of a sudden, they'll show you how you don't need that in some of the upcoming things. He doesn't say it anywhere in these sections. What is the variance of these resistors? Well, hold it. We know how to estimate the mean. Basically, we can get it within a certain value. Basically, we can get the standard deviation of the actual mean. But here, we're talking about the variance. Here's the sample variance. We had the variance of the mean value, but this is the sample variance. When you take a look at this, because this is in a continuous value, it's sampled, so it's discrete. You got a summation there. It's just an expected value of all these things right here. That would be the sample variance. The expected value of this, and here's the thing to note. When you, in the book, he has a discussion about this, how to calculate this, and he says it's tedious. Whenever he says tedious, it means it takes a lot of pages. That's what it basically means, a whole lot of steps. I don't know if you've read that in the book or saw it, but it's absolutely true. So when you do this right here, you actually get the expected value of, this is the variance, and if you look at this, it's the definition of variance. If you got samples, x of I, they're random variables. The sample mean will be the true mean right here. But after you go ahead and expand this whole thing and do it, it comes down to this. Now you'll notice that's n minus 1 over n, where n is going to be the number of samples that you take from this large times sigma x squared, where sigma x squared would be the true variance. The trouble with that is we want it to be equal to the true variance. We would like just sigma squared of x. And in fact, as n gets large right there, even though it's called a biased estimate, as n gets large, it does go to that value. It has to, actually, mathematically. Instead, we use this. Now, here's where people get a little crazy about it. They're saying this is called, instead we use this, and it's just referred to as the sample variance, but let me come to the next part. All right. So he says if we start taking 3 samples, here's how much the variance flies around. The variance of the 3 samples, assuming we know the true mean. Then he shows n equal 30, it's starting to, there's a much smaller range. And then finally, after all is said and done, this is the one you remember too, by the way. The variance of the sample variance, which I don't like, by the way. It's like, almost saying the square of the sample square or something. It just bothers me, the language. But nevertheless, you have a variance in the sample. And you know, you sample 3 again, 3 again, 3 again, you get different sample variances. With me on this? So when we take a look at the variance of the sample variance, we get this. Now, And he goes in the text, and if you want me to do this proof, ask me, and I'll do it in the office, because this is a long one. But I've not, this is one of these things, if you actually want to prove this, it's provable. I was messing with that last night. However, he just says it's tedious. What I would, the way you interpret that, it's unnecessary to know how to do that. You don't need to know how to do this. What you need to know is this formula. Now, this is important what I'm telling you, so listen. And write it down in notes. You're going to be asked about this, guaranteed, not maybe, guaranteed. All right, n, of course, is the number of samples you take. U to the fourth, right here, is the one. It's the fourth central moment. Now, you see that sigma to the fourth? That's the real sigma squared squared. It is the variance squared, which means, and it bothers me that they're not saying more about this, we have to know that. If we really know that, there's a lot of things that concern me. But when you look at this, the u to the fourth is the fourth central moment. Now, there's some very nice things about the fourth central moment when things are Gaussian. I don't know if you remember that. Remember, for Gaussian values, you can get higher, odd moments are always zero. I mean, odd central moments. Even central moments have the 1 times 3 times 5 times, it's really n minus 1 times sigma to the n. Do you remember those? You'll need to know that. So, for higher order central moments, if they're Gaussian, well, if they're zero, it's great, but they look, let me go back here. See this? This is always the fourth central moment they need. Well, the fourth central moment would be 1 times 3 times, and then it would just be sigma to the fourth. You follow me on this class? You almost want to commit that to memory. And then he says for Gaussian, it's that for uniform, you can assume without loss of generality that the range. And by the way, if they're odd central moments, they're always zero for anything, a uniform distribution or Gaussian distribution. And you can find out that this right here is the nth central moment. And really, you just have to worry about for even values, but the fourth central moment, I think, probably this includes that. So if you look at this right here, if it's the fourth central moment, it's going to be delta x to the fourth, that's the spread. And then that's 5, and it's 2 to the fourth, 16. But it comes down to a nice, easy thing. This is something you're going to not get familiar with because you'll be using it. But remember, for this formula here, the one thing that causes some problem is that u to the fourth. That's the thing you have to get familiar with when you're doing these problems. Yeah, I'm not, see this, these are actually how to compute them. I'm not going to ask you to compute these things. That's something you do with a computer. You don't need to do that. And then he gives an example of that. Make sure I know how to do that one. And then this homework. So I'm going to ask you next time to do these 3 homework problems too, for sure on Monday. I'll give you a quiz now. But I'm trying to tell you that the next stuff we're going to do after this is the probability density function of the sample mean. And here's where actually now we don't need the sample mean and we don't need the variance. If you guys remember yourself, why don't you fill up this row right here?